Okay, dear friends. Hello, everyone. I'm glad to introduce you to our friend and colleague Zoran Petric from Belgrade, Serbia. And we are glad to start our new seminar, which I asked Zoran to make, to participate, and to talk about his and Costa Dawson, if I spell it correctly, research on hypergraph polytopes. In general, I was interested in applications for our studies, in particular of complex systems on hypergraphs and potential invariants on it. But this theme is very deep and great in general, and it's closely related to our laboratory supervisors' research interest, which is related to some combinatorial polytopes. For example, permutohedrons and graphic hedrals and so on. So, dear friends, let's greet our friend Zoran for his speech. Thank you very much to everyone.
Спасибо, Коста, за эти приятные слова, тоже за приглашение участвовать на вашем семинаре. Я с большим удовольствием буду прочитать этот доклад. Спасибо всем участникам на семинару. Я уж давно не занимался этими поlytopами, но постараюсь, что вам этот доклад не будет скучно на этом докладе. К сожалению, мой русский не очень, и я поэтому перейду на английский. Could you hear me? It seems that it...
Everything's great. We're okay with English, and we are listening very patiently.
Okay, but I can't go to switch to another slide. I don't know why.
It just worked. Oh, it works.
Okay, it's okay now. Well, as it was announced, this talk is based on a joint paper with my professor and friend, late Costa Dawson. Well, we came to this point from proof theory. Well, we were interested in categorical proof theory, and in particular, some coherence problems were very much interested for us. And these families of polytopes, since they are contractible, could provide topological proofs of coherence of some kind of categories that we were interested in. And I will start this talk from the end. I would like to give you some intuition on what it is about, and I will start to talk about truncation of simplices. Well, could you see this picture? Is it too small?
No, it's great.
It's okay. Okay. Well, here at the left-hand side, you have a tetrahedron, a three-dimensional simplex, and the facets, the faces of codimension 1 are labeled by letters X. X is front left, Y is front right, Z is back facet, and U is the bottom facet. And in the middle, we have a picture where the edge between the facets X and Y is truncated. By truncation, I mean here intersection of the polytope by a half space, and this half space is such that it includes all the vertices, but the vertices belonging to the face we are truncating. So at this point, we have to label this new appeared facet, and I labeled it by x plus y. Well, we'll see whether it's good or not later. And at the right-hand side, we have a picture of the same simplex but the vertex sharing incident to facets x, y, and z is truncated, and we got a new facet, and at the picture it's denoted by x plus y plus z. Okay, and our goal, well, the question is how to encode the combinatorics of these polytopes. By combinatorics, I mean a face lattice of these polytopes, and the answer is that, okay, here we used for the tetrahedron just 4 letters, x, y, z, u, and we, for this one, this polytope in the middle, we added x plus y term, and at the right-hand side, we have a term x plus y plus z, and this is almost what we need to encode the combinatorics of the polytopes. The correct answer is obtained just by decorating it with some set vertices, set brackets, and adding some dummy elements. So at the left-hand side, now we have a family of sets, a hypergraph, which consists of singletons x, y, z, u, the same we had at the previous picture. And we have one dummy element added with this whole set x, y, z, u. And the role of this set we will see when we obtain geometric realization of face lattices we deal with. But for now on, this set x, y, z, u is here just to make the ambiental space where the polytope lives. Okay, and in the middle, we have added just a singleton whose elements, a singleton set with one element, with the 2 elements set inside, it's x, y in there, and at the right-hand side, we have added the set with x, y, and z in it. And the goal of this talk is to find some kind of machine for decoding these hypergraphs, and to find for a given hypergraph a combinatorial description of the underlying polytope. Is it clear?
Yeah, it is clear. Yeah, but I'm sorry, maybe I have a question. Maybe it is too early for this question.
No,
but
it's okay.
For example, if you have in your hypergraph, if you have, for example, x plus y and y plus z, then you should kind of truncate 2 edges, but the output depends on the order in which you truncate these edges.
Yes, of course, and it will come in later slides. I assume that truncations are done simultaneously. So if we truncate x and y and u, let's say, then we have to truncate a vertex also x, y, u. And this is something which is built in building sets. So it will come to this point later.
Yeah, I see. Thank you.
Is it okay?
Yeah.
So now we have just kind of intuition behind what we will do. Okay.
Thank you.
And okay, since you are all in hypergraphs, I don't need to define them, but just to check whether the definition is correct. Well, we have a finite set, and H is a family of subsets of this finite set alpha, and we assume that the empty set is not in H, and that whole set is covered by the elements of the family. And then this is a hypergraph on the set alpha. And well, one example is we have a hypergraph where we have three singletons X, Y, and Z, and one two-element set X, Z. And since all the singletons are in this hypergraph, we call this hypergraph atomic. I hope the terminology is correct. And this hypergraph is not connected since there's no hypergraph path from, let's say, X to Y. And I will say that the connected components of this hypergraph, or the connected components of the underlying set are X, the set XZ. This is one component, and the other is Y. We will need this terminology later. The other example is hypergraph with on four-element set X, Y, Z, U, and this hypergraph is not atomic. So since the singletons Y and U are not included, but this hypergraph is connected. And what is important for our machine? As input, we have a hypergraph, and I will start with ordinary graphs. It will be easier for me at the beginning, but as the output, I need to have a complete lattice of faces of the polytopes corresponding to this hypergraph. So I will start informally to explain what the constructions are, and after the constructions will be again hypergraphs, and they will denote vertices of the polytope. And if we omit one element of this hypergraph, which denotes the vertex, then we will obtain the edge incident with this vertex, and by omitting two elements, we will obtain a face of dimension 2, and so on. So I'll start with explaining what the constructions of hypergraphs are. And I always assume that hypergraphs or graphs are constructed vertex by vertex, and actually one can call them not constructions but destructions of graphs, whether it's more convenient to oneself. So I will start with this path graph with vertices X, Y, Z, U. And I assume that Y is added at the end of construction of this graph. So without Y, we have two graphs here. One is graph consisting of singleton X, and the other is the edge ZU. And so we assume that beforehand we have constructed this graph with singleton vertex X, and we have constructed this edge ZU. And initial diagram for construction will be this circle, which has dot Y inside of it, and these two rectangles are places where we'll put constructions of graph X and of edge ZU. And it is quite natural to take that X has only one, that single graph with a single vertex has just one construction, and this is circle with X inside. But this edge, keeping this pattern, has two possible constructions depending on whether we'll add Z as the last element in this construction, or U was the last element in this construction. So the diagrams for two possible constructions of the edge ZU are this one, where Z was last added, or this one where U was last added. And at the end, we have a construction, one construction of this graph, given by this diagram, and it is a hypergraph which has sets inside as many as circles are given here. So we have two singletons inside this hypergraph. This is the singleton X and singleton U. We have one 2-element set ZU, and we have one 4-element set XY ZU. And now I'll do this more formally for atomic hypergraphs. So the starting point is an atomic hypergraph, the hypergraph which includes all singletons of the underlying set. So in our example, we have a hypergraph H. It's a bit too long, but you can see that the middle part consists of three edges which make the path from the previous path graph. So you have here edges XY, YZ, ZU. These four singletons are here since we started to deal with atomic hypergraphs, and the others will be explained later, the role of this, but it has something to do with the previous question I got. Okay. So I have to define the notion for the starting hypergraph, for the initial hypergraph H, and beta, the subset of the underlying set. I define this H beta as a hypergraph that consists of all the elements of H that are subsets of beta. So in our example, if beta is the set of X, Z, U in it, then H beta consists of three singletons. This one is in beta, these three are subsets of beta, and we have this is a subset of beta, and that's all. And now this is a technical part. Well, the official definition of the construction of an atomic hypergraph. So this is an inductive definition, and it consists in three parts. The first part is just nothing, that the empty hypergraph has just one construction, and this is the empty set. And we have two cases, whether H is a connected or disconnected hypergraph. So in the case of a connected hypergraph, we start with one vertex of this hypergraph, the vertex Y, and restrict the hypergraph to the set of its underlying elements with the element Y omitted. And if we have a construction of such a hypergraph, which is named here K, then we have just to add the complete set, the underlying set alpha, to this construction to obtain one construction of the initial hypergraph H. And I will explain this through an example. It's almost unreadable now. And the second step considers the case where H is not connected, and H1 and A2HN are connected components, let's say, of this graph H. And KI is a construction of HI, then just the union of this construction makes a construction of the initial graph. And let's go through the definition using our example. So this was our graph H, and okay, this is the slide. Okay, our hypergraph H is connected, so we have to apply the step 1 here, and if we want to construct this hypergraph such that y, the vertex y, is added at the end, then we need a construction of the hypergraph H beta, which was the one from the previous slide, and we can see at once that H beta is not connected. Okay, and then in the second step we will find the construction of this graph H beta. And for a construction of the initial graph H, we need this construction of the graph hypergraph H beta and the complete the underlying set alpha. So the second step, in the second step, we have to construct graph H beta, which is disconnected, and for this we have to use the step 2 from our inductive definition. So we have to find one construction of this hypergraph and one construction of this hypergraph. And by using both these hypergraphs are connected, and we have to use step 1 from our definition. And here, by using step 1 and step 0 from our definition, we see that the only construction of this hypergraph is this hypergraph itself. And for this hypergraph, we again repeat the procedure, but we have to choose whether we'll leave Z to be the last added element or U to be the last added element. And again, by choosing one of these, we get to the graph which is singleton Z, and again it repeats step 1 and step 0 in order to obtain one construction of this hypergraph. So the two possible constructions of this connected hypergraphs are these two. And one construction of the graph H beta is this one. For this, we've chosen that Z is the last added element in the construction of this hypergraph. So the initial hypergraph has this as one construction, and this construction was the same as the construction of our graph, which we done informally at the beginning. This is the same hypergraph as this one. And we can see now that the hypergraph H from our example and this hypergraph, which does not include 3-element sets and 4-element set in it, have the same constructions, because the procedure will be completely the same when we apply we start with the same beta as in the previous example and restrict this graph H1 to the set beta, we will obtain the same hypergraph as in the previous case. So it is easy to see that the constructions of a hypergraph and a hypergraph which is obtained from the initial one by closing or saturating according to this rule. This rule says that if we have two elements in our hypergraph which do intersect, then their union must be also already in the hypergraph. So if we started with the hypergraph H1 and we want to saturate it, then since XY and YZ are in this hypergraph, then we must have inside the three element set X, Y, and Z, and also since Y, Z, and ZU are inside, then we must have three elements set Y, Z, and U. And then at the end, we obtain that the set X, Y, Z, and U must be also inside, and this saturation produces from the hypergraph H1 the hypergraph H from our example 4. And now we can introduce the notion of a building set. A building set is nothing but an atomic hypergraph which is closed to this rule. And the other name for building set is just atomic saturated hypergraph. So we have that the saturation of an atomic hypergraph is the intersection, so it is the smallest saturated hypergraph containing initial hypergraph H. And for two atomic hypergraphs, we say that they are cognate when they have the same saturation. So we have an equivalence relation on hypergraphs. And it is easy to see that cognate hypergraphs, because of our definition, inductive definition, have always the same constructions. And from constructions, we know that we can produce phase lattices and then geometrically to realize those phase lattices. So the polytopes corresponding to cognate hypergraphs will be the same. So polytopes cannot distinguish cognate hypergraphs. So in the equivalence class of cognate hypergraphs, we have a canonical representative, which is given by a building set, by such saturated hypergraph there. But maybe for people who are interested in hypergraphs and recognition of hypergraphs by polytopes, it could be interesting the following question. It comes to my mind just today, and I'm not sure. I think that the answer is positive, but it could be interesting because you see here, we have our hypergraph H, which was actually a building set. It was saturated. And it is somehow maximal in this equivalence class. And here we have graph H1, hypergraph H1 that belongs to the same equivalence class. And it seems that it is a smallest element in the class. And if the answer to this question is every class of cognate hypergraph closed under intersection? If the answer is positive, then we always have some kind of interval starting with the smallest hypergraph in the class and ending in the building set. And I think it could be interesting for you. Well, maybe it's easy to answer and someone could have the answer to this question up to the end of this talk. I don't know. Now, this is the geometric explanation for saturation. The question asked by professor at the beginning of my talk. Well, if we have a hypergraph that contains two element sets and which intersect in one point. So, for example, if we have a hypergraph that contains the set xy and the set yz, and this means geometrically that we have to truncate edges between x, y, the faces x and y, and the faces y and z. In a three-dimensional case, x, y, and z are facets. And if the truncations are performed simultaneously, then we will obtain a vertex in the polytope that is 4-valent, and the polytope won't be simple anymore. A simple polytope in dimension n has exactly n facets incident to each vertex. And here, a vertex incident to 4 facets would occur. So if we truncate this edge and this edge, we have to truncate the vertex first. Okay, and in this situation, we keep the simplicity of the polytopes, even if we do truncations simultaneously, which is indicated by the hypergraphs. And now I will explain our motivation for the term constructions and then for this notion. Again, this has something to do with 2 our examples from above. So I'll start with an associative operation and a term where the instances of the operations are labeled by x, y, z, and u. So we have 5 letters, A, B, C, D, connected with these binary operations, and there are no brackets since the operation is associative. And so somehow we want to make a continuous resolution of these terms. So algebraically, this is just one point, and homotopically, well, this will be also just one point since the polytope is contractible. But we'll start to make first all the possible constructions of this term, which has to do something with all possible complete of this term. And this will produce the vertices of our polytope. If we consider the instances of this binary operation here and the neighborhood, the graph of neighborhood operations, we obtain the graph from our initial example. So we have a path graph consisting of x, y, z, and u vertices, and one path between them. So one construction of this graph corresponding to one possible bracketing of our term. So, for example, if we have our construction from first example, then this construction says that y is the terminal operation in this term. That's why we have brackets all around there. So y is the terminal operational symbol. and then this graph, the graph has split it in two parts. One is a singleton X, so we have then brackets between A and B here. So X was the terminal symbol left to the Y. And here we know that Z is the terminal symbol. So we have in the bracket right to the Y, we have that the terminal operation is this one labeled by Z. And at the end, right to the Z, we have a terminal operation, which is the unique operation, the one denoted by, labeled by U here. So, and here we reach the limit of standard syntax. Standard syntax can't go beyond this. And we would like to make something more. And we put these constructions, in other words, these terms in vertices of a polytope, and then use subsets of these constructions to denote edges and facets of the polytope. All in all, there are 14 constructions, capital number, 14 constructions of this graph. And two such constructions are connected by an edge. Edge is denoted by a construction with one element omitted. And two such constructions are connected by an edge of this polytope. If the terms corresponding to constructions differ only in one application of associativity. And the intersection of these two constructions should contain three elements. For example, here we have another construction of this graph. And this construction corresponds to this bracketing. So we have applied one associativity inside these the right-hand side brackets. And this vertex is connected by vertex chi, which is the same as this one, just Z here in this singleton is replaced by U. So they differ only in one element. This intersection of K and K prime consists of three elements, and this intersection labels an edge containing K and K prime. Okay, it's here at this slide, we have that the edge between K and K prime is labeled by this hypergraph. And here is the picture. We have at the top level, we have here the construction K. Here at the bottom, we have the construction K prime, and here is the edge. And in terms with letters A, B, C, D, this corresponds here just to two complete bracketing. These are vertices, and this edge is denoted by a term in which one pair of corresponding brackets is omitted. And this term corresponds to this subset of K and K prime, actually the intersection of K and K prime, and every such subset is called construct. And constructs are important for us because they will make a face lattice of a polytope. So there is a condition that every constant should contain every connected component of the set underlying the initial hypergraph. So connected components, since the initial hypergraph was connected, the connected component is this four-element set X, Y, Z, U. So we, for faces of our polytope, the faces of our polytope will be denoted by subsets of hypergraphs which must contain this set X, Y, Z, U, and this is the only we have here. And when we come to faces of higher dimension, the analogy is complete. So we have that two vertices belong to the same face of dimension 2 in a polytope when their intersection contains two elements. For example, we have here the constructions K prime and K double prime, and the intersection of them contains these two elements. It is a construct since it contains the set X, Y, Z, U, the underlying set, since this is the unique connected component of this set. The graph, the hypergraph was connected. And here we have a picture of a polytope for which we still do not know whether it exists or not. But here the vertices K, K prime, and K double prime are presented. They all belong to one two-dimensional face, to one facet. And if we denote the facets of the initial tetrahedron as at the beginning by X, Y, Z, U, we can easily read what from this picture, what are the elements of these constructions K, K prime, and K double prime. Now we come to the definition of the abstract polytope. So when we start with an atomic hypergraph H, it could be a building set, but it's not necessary. And the abstract polytope of this hypergraph is denoted by A of H. And this is the coset whose elements are all the constructs of the initial hypergraph, and they are ordered by the opposite of the converse of the inclusion. And we have to add the bottom element just to have an abstract polytope, to have something which could be a face lattice of a polytope. And in our example, in this illustration, we have just a part of the abstract polytope of the initial hypergraph H, this path graph from the beginning. Here we have just 3 vertices, and actually this space lattice has 14 vertices here. Here we have just 2 edges. So at the dimension -1, we have 1 element as usual. Here at dimension 0, we have 14 elements. Here at this illustration, we have just 3 of them. K prime and K are incident with this edge, face of dimension 1. K and K double prime are incident with this wedge. This edge and these 2 edges are incident with this facet. At the top level, at dimension 3, we have the whole polytope singleton set. And another approach to the same mathematics is given in Postnikov's paper, permutohedra, associahedra, and beyond. And he has another kind of definition of the same family of polytopes. And he starts with building sets, so atomic saturated hypergraphs. And he defined nested sets of this building set as follows. His definition has 3 steps, and we'll go through an example by this definition again. The first step says that when we have 2 elements of potentially nested set N, the then either one is included in the other or other way around, or they do not intersect. The second step in his definition says if we have a family of more than one elements belonging to this set N, which are all mutually disjoint, then their union does not belong to the initial building set. And the first condition is that N must contain all maximal elements of B. This corresponds to our condition that our construct must contain all connected components of the underlying set of the hypergraph. And I'll show you now that our construction came from previous example. When we start with the building set H from this example, is a nested set by Postnikov's definition. So first we have to check whether this step 1 works. So we have here that X is disjoint, singleton X is disjoint from singleton U, it is disjoint from two element set ZU, and it is a subset of the fourth set in this family. And the same holds for U. So singleton U is a subset of the second, of the third and the fourth element in this family. And the two element set ZU is a subset of the final element of this family. So the first condition is satisfied. And for the second condition, if we have two mutually disjoint elements, such as singleton X and singleton U are, then two element set XU is not in our starting building set H. And we know that it is not there because all two element sets of this building set H are the sets XY, YZ, and ZU. So XU is not, X and U are far away. So they are not the edges of the initial path graph. And we can check that the second condition is satisfied for all these four elements. And at the end, the maximal element of our building set is this one, and contains this maximal, the only maximal element is this one. So N contains it, and this is a nested set. Let me see. What's the time? Okay. Is it okay?
You have lots of time, as much as you want.
No, it's too much. 10 minutes or 15 minutes more, not. Then I'll stop. It's too much for one time. Okay. Then state complex. Let me see. Okay. And first proposition I have here says that a nested set is the same as the construct when we start from a building set, when our hypergraph is a building set. And the nested complex is a poset of all nested sets. So we have that this poset is the same. This proposition 2 says that this poset, when we reverse the order in it, is the same as our abstract polytope on the hypergraph B. Just from this abstract polytope, we have to remove the bottom element, this start to be added at the beginning. So this proposition 2 is just the corollary of the proposition 1. And this simplicial complex is interesting for us. So this poset is not simplicial complex, but it is easy to turn it into a simplicial complex. All we have to do is to remove all the maximal elements from every nested set, and this poset then will be a simplicial complex. So simplicial complex is a family of sets which is closed under subsets. So we have, if it is finite, and if we have finite sets alpha n to alpha n, and power sets of alpha n to alpha n, then the union of these power sets is just a simplicial complex, and alpha n to alpha n are maximal simplices in this simplicial complex. And there is another alternative approach to the same notion, and it is given in the paper by Feichtner and Sturmfels. And there is a similar notion, not quite the same. And another approach to this similar notion is given in a paper by Carr and Devadoss. And for the historical perspectives, one can see the papers by Fulton and McPherson, the Concini-Procesi, Gaifi paper, and Feichtner and Kozlov's paper as well. And we came now to geometric realization. So we have posets, and it is a question whether such polytopes exist whose face lattices are isomorphic to posets produced by our machine producing constructions of hypergraphs. And the answer gives this proposition 3 here, and it says that if we start by a hyperplane given by this equality, and that's why I told at the beginning that this set X, Y, Z, U gives the ambient of the polytope. So this hyperplane is the ambient where the polytope lives. And it is obtained by intersection of these half spaces. So they are produced, take an element of the hypergraph of a building set now. So we need to start with the saturated, atomic saturated hypergraph with the building set. And then if we produce a half space by this inequality, so we sum all variables indexed by elements of an element of our hypergraph and make this inequality, then the intersection of these half spaces in this ambient hyperplanes gives a polytope whose face lattice is isomorphic to our abstract polytope from of hypergraph H. And the family of obtained geometric polytopes are called in our paper hypergraph polytopes, but more usual name are nestohedra. And there is, of course, another way how to realize these polytopes through Minkowski's sum, and it's given in Postnikov paper cited above. And there is a key lemma for this fact. Actually, this lemma shows that if we start from a construction and intersection of all hyperplanes corresponding to the elements of the construction, this intersection gives a vertex of a polytope, and all the facets incident to this vertex are carried by hyperplanes that correspond to all the elements inside this construction. And well, I thought to prove something in this talk, and I could make this proof, but maybe it's too late and you are too tired. And please tell me if I should go through the proof or just skip it.
I think everyone is not that tired, and we are very interested in proof. If you still have time, of course, Professor Petric.
Okay, then I'll prove this, and I think I'll finish with this. But, okay. So we have such a statement. We have an index set I, and we have positive real numbers indexed by this set. Non-negative, okay, real numbers. And we have incomparable subsets of this index set denoted by x1 to xn. N is greater or equal to 2. So there are at least 2 subsets which are incomparable with respect to inclusion. And the statement is if for every element for every index from 1 to n, we have that this sum of real numbers is less or equal to 3 to the power of the set xj. So we have to count the number of elements of the set xj. Okay. Then it holds that this sum is strictly less to 3 to the power of the initial index set I. And the proof goes by induction on this n. And the basis is when n is equal to 2. And we have to start with this sum. I belongs to I, and I is here just the union of x1 and x2. And we have, okay, and in the case when x1 and x2 are disjoint, then we have that here is just equality. And in the case that they do overlap, then we omit at the left-hand side just some positive real numbers in the sum. So we have this inequality here. And our assumption, this one, says that this sum is less or equal to sum of this 3 to the power of the cardinality of x1 and 3 to the power of cardinality x2. So in this line, we use just the assumption. And well, assume that the cardinality of x1 is n1 and the cardinality of x2 is n2, and assume that n1 is greater or equal to n2. So we have that this sum then is less or equal to 2 times 3 to the n1, and 2 times to 3 to the n1 is less than 3 times to the n. This 3 comes from here. So this line comes from the fact that 2 is less than 3. Nothing else. Okay, and here in this line, we use the facts that x1 and x2 are proper subsets of the union x1 union x2, since they are incomparable. Okay, and this finishes the basis of this induction. And in the case when n is greater than 2, then let me say that here it's not only an assumption that x1 and xn are subset of I, but that they cover I. That's what I omitted in the statement here. So if n is greater than 2, then we start with the union of first n minus 1 sets in this family. So let X be the union of the family of n minus 1 sets. And by the induction hypothesis, we have that it holds that sum of these real non-negative real number is strictly less than 3 to the power of the set X. And now we have two cases. First is when the last set Xn belongs to X. This means that the union of all sets is X. Then, since we have that this sum is less than 3 to the X, and this sum is the same as the sum when we have here I instead of X, then we are done. And in the case when Xn does not belong to X, it holds that also if Xn is not subset of X, it also holds that X is not subset of Xn since all the elements x1 to xn are incomparable, and if X is subset of xn, it holds that all these are subset, all x1 to xn minus 1 are subsets of xn. So we have that X and xn are incomparable, and again we can obtain what we did in the basis of this induction, and so this statement holds. And almost very easy corollary of this lemma is that the face lattice of the obtained polytope by these intersecting half spaces is the polytope with the same lattice as the lattice of our abstract polytope A of H. So, let this be the last slide. Okay, I have to explain the interval simplex. Kostya asked me about this interval. Well, if we start with the finite non-empty set, and we consider all atomic saturated hypergraphs building sets, connected building sets on alpha. If the initial hypergraph or building set is not connected, then we have actually a product of polytopes that correspond to connected components of such a hypergraph. So we can concentrate only on connected atomic saturated hypergraphs, and if we take all such hypergraphs, they make a meet semi-lattice, since the intersection of two such hypergraphs is again a connected saturated atomic hypergraph on the same set alpha. And the bottom element of this lattice is a hypergraph that corresponds to simplex. It consists of all singletons of elements of the set alpha and the set alpha at the end. And the set alpha serves here just to make it connected. And at the other end, the top element of this mid semi-lattice is a hypergraph that corresponds to permutohedra. In terms of truncations, we have here truncated all the faces of the initial simplex. So we truncate all the vertices, all the edges, all the faces of dimension 2 up to the dimension d-2, where d is the dimension of the polytope. And in between, we have many interesting polytopes in each dimension, and our example was an example of associahedra, and we have cyclohedra inside and many other interesting polytopes which can serve for proof of coherence, and which can serve also to recognize loop spaces as associahedra do, and so on. I think it's enough for one day. I'm sorry, I thought to talk less than an hour, but it was much more. Спасибо большое.
Спасибо вам большое, профессор Петрич. Давайте все поаплодируем нашему докладчику. Да, спасибо большое за большой содержательный доклад. Было очень интересно. Ну, в частности, in particular, thank you very much for touching on the applications and on redefining. You said that you started from the end, but it felt very natural and obvious as the talk went by. So does anyone has some questions? Ivan, Anton, Matvey, Alexander, does anyone has questions?
Yeah, I try. Actually, I'm sorry. I want to understand this last. Yeah, maybe I just ask. So you consider the set of all, actually the set of all building sets. Is it correct?
Yes, all connected building sets.
Yeah, all connected building sets
All connected
on a given set.
Just to meet the products of polytopes.
And this is so it is just, or the order is given by some inclusion, like natural.
Yes, order is natural by inclusion.
And so you think that this is some good, I mean, this is some good partially ordered set in some sense.
Well, if you take polytopes up to combinatorial equivalence, then it is not, because you have combinatorially isomorphic polytopes which are produced by different building sets.
I see. Yeah, but even if we do not consider polytopes, if we consider just building sets as
if you consider
elements,
just building sets, then it is okay.
So this is some partially ordered set. Okay, this is some finite partially ordered set, but I don't understand if it is also some. So you say that it is the phase lattice of some n-dimensional polytope.
No, every element of this partial order belongs to some. No. The level.
But you don't know. Well, you do not state that this partially ordered set itself is the deposit of phases of a polytope. This may be not true.
It is written here, for every H belonging to this lattice, we have an abstract polytope, and then we have its geometric realization.
Mm-hmm. Yeah, right.
So H is big lattice whose elements are building sets.
Mm-hmm.
And you have a polytope that corresponds to each of these building sets. These polytopes are not necessarily combinatorially different.
Yeah, I see. Yeah, but I was just wondering, so you have this set of building sets. It is also some partially ordered set. So it is interesting.
Yes, they also make a partially ordered set.
Yeah, but this may be not an abstract polytope, not spherical. And this is something strange.
Yes, it's something strange. It's not realizable, I think, as a polytope.
So this simplex. So this is what you call simplex permutohedron, right?
Yes, that's the interval simplex permutohedron.
Yeah, thank you. That's interesting.
And you can go beyond, but it was illustrated at the first slide of the presentation. This polytope is not a nestohedron. It's obtained by new kind of constructions, since we start with the permutohedron and took the simplicial complex that corresponds to, well, it's a dual of the face lattice of permutohedron. And then we start with the building set on this simplicial complex. Here we have a definition of it, and this building set is such that we produce the permutohedra. So this is a more complex structure.
So you somehow combined.
This has something to do with Kostya's question about more complex structure on hypergraphs.
I see.
So it's not a hypergraph, it's not a building set on a set sum, but it's a building set on a simplicial complex.
I see. Yeah. And in this manner, you can obtain permutohedron.
Yes, in this a simple version of Kapranov's version of permutohedron is not simple polytope, and this one is simple.
I see. Yeah. So, but actually, so all constructions, in all these constructions, you get some convex. Actually, these are some convex polytopes and their face lattices.
Yes.
Okay, yeah, because with Kostya we are interested in some, like in constructing non-partially ordered sets which are not spherical, not Euclidean, and so on.
These are always simple polytopes. Always as a result, since the face lattice since the lattice we obtain is always isomorphic to a simplicial complex, so you put it upside down, and or you can study simplicial polytopes or put them upside down to obtain simple polytopes, but that's always the case.
I see. Yeah, thank you very much.
Thank you very
much. Very nice.
Для вас просто и SEO.
Yeah, does anyone else has some questions?
Well, yeah, perhaps I can ask one. Zoran, did you investigate your class of polytopes for having Delzant realizations? You know, Zalevinsky, I think he proved that
they are all Delzant realizable, since you always start with simplex, which is Delzant, and then you can then you have just to truncate it. You can truncate simultaneously, but you can truncate in a clever way, one by one. First truncate vertex, and then truncate edges, and so on. So it's always obtained, and then you can choose these hyperplanes bounding the half places, so that you obtain the Delzant polytope. So you can do this.
So you can choose such clever truncations that they produce. Yeah,
yes, definitely.
Realization.
So there is a theorem by Lemma by Koreans which says that this.
Oh, great! That kind of generalizes the result of Zalevinsky, who proved that nestohedra have Delzant realizations, and this is kind of general. Yeah, great. Thank you, Zoran.
You're welcome, пожалуйста.
Yeah, thank you for all your questions. Does anyone else has some? I was really curious is those constructs on hypergraphs can inherit some of their internal structures or dynamics. Probably you could build some add-ons on your polytopes, like paintings, for example, and they would help us classify some dynamics on polytopes, on hypergraphs more precisely. As well, it might help us distinct cognate polytopes, for example, if they are built from differently saturated hypergraphs. If my question makes any sense.
Yes. Thanks for your question. Well, you mean coloring all the faces of polytopes in order to obtain different polytopes corresponding to cognate but not same hypergraphs?
Yes. For example, ASC, different hypergraphs or different atomic hypergraphs, yes.
Yes. Well, maybe we are too much stuck to this obtaining simple polytopes, and that's why we have this saturation always in mind. Just not to leave the class of simple polytopes. Otherwise, maybe you can make a definition of construction which gives you other kind of lattice which is not necessarily isomorphic to a simplicial complex. And then to work with something like this, or to remain in the family of simple polytopes and then just use colors indicating somehow the order of truncation or something else. I don't know. Well, if you have a hypergraph, then as Anton told at the beginning, then you don't know which truncation should be applied first. So if you have XY and YZ in your hypergraph, they are equal there as sets, as subsets, as elements of families. So you can't say which comes first. So I don't know what to paint at that moment.
That's I forgot about that they are simultaneously truncated, and that's why it's harder to make a connection.
The problem is here in this picture.
Yeah, Kostya, I think that it is very important from this talk that maybe you should concentrate not on general hypergraphs, but on building sets, actually, because this construction, like these polytopes are built from building sets. Maybe this kind of hypergraphs gives you some additional structure in your studies.
Yes, it turns out since all cognate have the same polytopes, then it's sufficient to take into account just building sets. You don't need other. But it only shows that you can repeat the same construction with the same procedure, which gives you the same constructions starting from hypergraphs which are not building sets. You have no, in our definition of constructions.
That is why you saturate them.
In our definition of constructions, you need not to saturate them to start with the construction. And the result would be the same. I don't need to saturate my graph to start with this inductive definition. I can apply it to any atomic hypergraph. But the result will be the same as if I start with already such building cell, saturated one.
I see. Yeah, that's important. So, friends, do you have any additional questions? Okay, seems like there's no one in chat also. Okay, Zoran, then thank you very much. It was a joy to listen to you, and I've harvested several good ideas for myself. I hope everyone did so too. It's actually a lot of things to. I've read your paper several times, but still I got more understanding after your talk, of course. Thank you very much.
Спасибо вам всем большое.
Да, спасибо
Пока.
вам.
До свидания.